So there you go. The recording has started. So once again, I would like to welcome Dr. Puvan to begin his invited lecture entitled Soil Water. So the stage is yours. Please. Thank you.
Okay. Thank you, Dr. Young. So good evening to all. So for today's lesson, we are going to learn soil water. And soil water is one of the most important factor in determining the soil health and as well as soil fertility. Basically, soil water actually controls almost every process in the soil, like the nutrient movement, biological activity, and plant growth. And we will go deeper a bit later in this the slides. Okay, for today's lecture, we are going to cover the functions of soil water, functions of water in the plant growth, what is water holding capacity, and then soil water, we can break them into three stages, types, and water movement. So later I will show you and explain what are the terms or different stages, types, and also the movement of water according to each stage. So that the topic 4, 5, and 6 is very important, but we can summarize it using one infographic picture. It's taking a bit to load for the screen. So if it doesn't load, just let me know, okay? Okay, so we look at the functions of soil water. Uh, Soil water is not just a moisture, but it's a reactive medium that drives almost all soil and also plant processes because it can help in weathering of minerals, decomposing of organic matter, and soil structure as well can be affected by the presence of moisture in according stages. So it can help particles to form aggregates, to form different structures and the pads that it can form. So, but it's very crucial for the soil water to be balanced, meaning where the water will be stored in the pores of the soil, but it's not only for water, but air as well need to be inside the pores. So an ideal soil usually have 50% of water and 50% of air in its pore. So if it's let's say water is higher, then it will cause problem for root respiration, and vice versa. If water is lower than 50%, then meaning air is more, that means water is less readily available for not only plants but also the microorganism that is going to do metabolism, its metabolic process that depends on water. And too much of water can also cause leaching of nutrients. One unique thing about water is that they can adhere to each other to form structural aggregates. So this one I will explain more in later slides. So water actually can do two things. It can adhere and it also can become cohesive. So what is that? We'll look into in the later slides. Soil water participates in numerous chemical reactions that release or ties up nutrients, create acidity, and wears down mineral. Just as I said, it can help for weathering processes. And if you recall in earlier slides, I think earlier topics you have learned about hydrolysis, hydration, carbonation, and everything. And most of these processes require water for it to occur. The soil-water relation determines the ecological functions of soil, such as rate of water loss through leaching and evapotranspiration, the balance between air and water in the soil pores, and the rate and kind of metabolism of soil organism. Finally, the capacity of soil to create and provide water for plant growth. So each processes like transpiration requires water. Even the movement of nutrient into the soil requires water as a medium. So this is an infographic of hydrological cycle. So the water comes from precipitation, and when it reaches the soil, on top of the soil, it infiltrates and moves into the soil water storage through percolation. And this can be divided to move to groundwater, or it can just run off to the nearest water bodies such as stream, ponds, and lakes. And what about waters that doesn't infiltrate? Let's say there is no proper vegetation and due to gravity action, so the water will just go through surface runoff. Okay, now we are looking at the specific functions of water for plant. So water makes up 50 to 90% of plant tissues. So without it, no physiological processes can occur. The key roles of water for plant growth is ultimately turgidity, because it helps to keep the stem upright and leaf expanded. If no use, your plants, if it lacks water, the basic symptom that we can see is wilting, ataupun kita panggil sebagai proses layu lah, because due to the lack of water inside the cell. And secondly, photosynthesis, it supplies hydrogen for forming carbohydrates. So the hydrogen comes actually from the water that is being split when photosynthesis occurs. And transpiration is the cooling of plants and maintains nutrient flow. So transpiration is very important in where water is being removed through the stomata just to create pressure for water to be taken up by the plant. So if you have aquarium at home, how do you normally clean up your aquarium? So you normally use a tube and you just suck at the one side so the water flows out, right? So that you are not going to keep on sucking the tube until the water comes out, but you only suck it to create the air pressure, and the water will flow out until all the water from the aquarium is removed. So basically, transpiration is what we have been doing to clean up our aquarium, but the plant does it by, in a way, we call it transpiration or evapotranspiration, where water is sucked out or removed out using the energy from sunlight and being removed through the stomata, and this then creates a pressure called turgor pressure to increase the water that is being pulled up by the roots from the soil. Okay, and then next is for nutrient transport, where water is the medium to dissolve and as well as carry minerals to roots. So basically, water is what blood does for us human, for plants. And finally is for translocation. So it moves sugars. When photosynthesis is done, the byproduct is moved and sent to the specific location inside the plant by water. So I can say that water is both the fuel and also the transport system of plant. So because they are the basic materials for some processes, but they also are the one that is going to carry nutrients and also the byproducts of photosynthesis and sending them to specific locations such as the fruits, leaves, and other parts of the tree. When we learn about soil water, we need to understand water holding capacity, or simply we say it as WHC. So WHC actually tells us how soil holds the water, and it also explains us why not all of that water that is inside the soil is available for the plant. So water holding capacity is the total amount of water a soil can retain and potentially supply to the plants. So, or in the technical definition, a measure of quantity of water that can be retained or held by soil. So example, amount of water can a particular soil retain, and not all the water film surrounding a soil can be drawn by plants. So only a portion of the total water holding capacity of a soil can be said plant available. So water holding capacity refers to the ability of the soil to hold water, but it doesn't tell us how much can it give to the plants, because the soil that, but the water that the soil is holding is actually not for the plant, but it is for the ultimate reason is for the soil to maintain its state as a soil. So because soil undergoes genesis, so there's formation of new things, destructions of something, older things, and water is needed. But some of the water can be given, or a portion of water can be given to other things, such as the microorganism and also the plants. So to really know how much water that this particular soil can give, then we need to look at the types of, stages of soil water. So that will be in the following slides. A healthy soil will usually have high water holding capacity, and usually healthy soil have high organic matter. So for every 1% of organic matter, it can, okay, I'm sorry, I need to pause for a while because the azan is being said here. Is it okay, doctor?
Yeah, sure. Let's give a pause. Sure.
Okay, I think I can resume now. So you still can see my slide, right?
Yes.
So I was at, okay, for every 1% increase in organic matter, we can increase the available soil water by 20,000 gallon for an acre of soil. So usually that's why we associate with organic matter content with water holding capacity. But remember, water holding capacity doesn't mean plant available water will be high. So because I believe you have learned about sand, clay, and also silt. So maybe I can ask the students, one of you maybe can turn on your mic and answer. So among sand, silt, and clay, which one will have higher water holding capacity?
Clay.
Okay, clay. So meaning clay stores more water, and if we arrange them, it's clay, silt, and followed by sand. So imagine you have 3 cups of water with sorry, 3 cups of soil, sand, silt, and clay, and I make an hole down there. And if I pour water to all these 3 cups, which one will be dripping? The water will be dripping out from it very fast. Surely it's sand, right? But the water in uh, the cup that has clay will be held by the clayey soil. So there will be very minimum or even none of water being dripping out. So this actually shows the holding capacity of the soil, the type of soil. But imagine the water that is actually dripping out. That is the water that can be taken by plants without giving any or using any energy. But to be honest, among the three, which one will give is which one will have plant available water? Just a like guess because you haven't learned this yet. So among these three, because you know sand, silt, clay, and how they function and why they are different. So basically, for those who don't know, it's soil texture, three types of soil texture, different particle sizes, and clay having the smallest sizes. So they have very fine pores. So that's why they have, as your friend said, they have very high water holding capacity. So now my new question is, which one has higher plant available water? Can I say sandy soil have higher plant available water, or is it actually clay soil that's having higher plant available water? Can anyone take a lucky guess?
Sand soil.
Why do you think sandy soil have higher plant available water? Usually when I ask the follow-up question, you will be missing, right? Okay, I believe it was Muhammad Nuramin said sandy soil having more available water, right? But now you imagine that as a cup, right? Now imagine it's in the field. Rain pours down the water, and before the water being stored in the soil, it moves very quickly. It drains very quickly and moves to the water body. So my question is, your plants that you are planting is on the soil or inside the water bodies? Of course, it's on your soil, right? So imagine now, on the soil, the plants uh, doesn't even have enough time for them to pull up the water using transpiration or from the fine root hairs. But before they can do that, water is gone from the soil. So we cannot say low water holding capacity equals to high plant available water, nor that we can say high water holding capacity equals to better plant available water, because there are other factors that we need to take into account. And the only data or the only measurement that can tell us which type of soil can have higher plant available water is actually the pressure itself. So we can measure it using kilopascal, or we can use bar. So that one, and that is the one that is going to tell us, okay, this soil is having enough water that the plant can take up. And to make it correct, it's not just enough. The water needs to move in a specific speed so that the water can be available to the plants. If it's too fast, plants cannot take it up. The water, and even the soil cannot hold it for so long. It will just drain out. But if it's too slow, then the plant needs extra energy to absorb it. Okay, with that, we are going to look into the measurements. Okay, so before that, some of the factors that affect water holding capacity. Okay, so the easier way for you to remember is water holding capacity is talking about the soil itself, whereas plant available water is talking about the plants, the water in reference to the plants. So we have two things to refer here. One is the soil itself. So when we talk about the soil itself, we say it as water holding capacity. But when we want to refer for the soil water in reference to the plants, then we need to look at the plant available water. Okay, for the soil itself, the water holding capacity is dependent on soil texture. So finer texture has higher water holding capacity. In other words, clay has the highest water holding capacity, and sandy soil have the lowest. So silt or loam is the intermediate. So usually I teach my students just to remember the maximum and the minimum. So if you remember, clay is the highest and sand is the lowest. Loam or silt is usually in the middle. For organic matter, so as I said, 1% of organic matter can help to store 20,000 gallons of water. So surely soil that has higher organic matter will have higher water holding capacity. And if you want to put up to organic matter's weight to its ratio for water holding, so organic matter can absorb water up to 30 times its weight. So imagine you have a sponge that that can hold more water. So organic matter is like a sponge. So usually I ask my students, usually I do this for my diploma students. So let's say I have a bottle here, right? So this bottle, let's say the maximum amount of water I can store is 100 ml. So let's say this bottle, I can store 100 milliliter of water. So my question is, how can I improve the amount of water that my bottle can store? So, okay, for those that cannot see, I just, let's say, this is actually, I think, 2 liters. So to make it easy, let's say it's 1 liter. So the maximum capacity of this bottle is 1 liter. So can I increase in a way that this bottle becomes able to store more than 1 liter? Do you have any idea? In a way, I can improve that this bottle, which is limited for 1 liter, I can actually store more than 1 liter. Is there any way for me to improve the amount of water that is being stored inside this 1 liter bottle?
That doesn't sound possible, right?
But actually, it's possible.
Okay.
So remember, I said organic matter acts as a sponge, right? So imagine I fill in 1 liter, and then I soak another, let's say 2 or 3 sponges. I soak them in water and I store it inside here. So actually, without buying a new bottle, I mean, we are not going to do that. You are not going to bring water bottles with sponge, but actually, you can somehow do magic, and when you pour it out again, you will have more than 1 liter of water. So this is why I'm saying organic matter is very, very important for improving water holding capacity. Like your friend said, sandy soil have low water holding capacity. So to solve the problem, we can add organic matter. So they improve the pockets, or they are like sponges that help the soil to hold even more water. So it's like giving them extra spaces for them to hold water. And soil mineralogy also can affect water holding capacity. So soil containing clay mineral usually have higher water holding capacity, for example, like vermiculite and montmorilonite. So because montmorilonite and vermiculite have open lattices where there is no bonds, I'm not sure they have learned these topics or not yet, Dr. Yong.
Not yet. It will be in the next week's lesson.
Okay, so so I'll just give you a teaser of it. So vermiculite and montmorillonite, so they are 2-to-1 lattice where they have higher negative charge density, and there is no charges in between. So I think Dr. Yong will show you the diagram, the full diagram. Whereas compared to kaolinite, it's a 1-to-1 lattice. It's very small, and it's very tightly bonded. So there is hydrogen bond in between. So that's why water cannot be contained more in kaolinite compared to vermiculite and montmorillonite. So I think maybe you need to know what is each of that, and then you get the essence of this. Okay, take some time to digest the pictures that's in front of you. So just forget about the words that's stated here. So you can look at the first 3 pictures on your right, and then take a look at the picture on the bottom. Okay, water is actually held by 3 bonds. So the 3 bondings that is very important for us to know when we deal with water is first the hydrogen bond. Next is the cohesive bond, and finally we have the adhesive bond. So hydrogen bond is the attraction between hydrogen of one water molecule and the oxygen of another. So H2O is actually water, right? So a molecule of water usually looks like this. So there's a 1 oxygen atom in the middle with 2 hydrogen atom to the sides. And water, kalau korang pernah dengar this term or peribahasa, you will say air dicincang takkan putus. It's because chemically they will get bonded through hydrogen bonding. And why this happens is because water is a dipolar molecule. So it has slightly negative side on the hydrogen, and water is a dipolar molecule, and they have one section which is a bit positive compared to the other, or we can say one section is highly negative compared to the other. Overall, they are actually there's no ionic any ionic charges, but the positions of the lone pair in the bonding causes water to become dipolar. So do you know where is the slightly negatively charged area, and where's the slightly positively charged area?
Students, anyone who want to answer this question? Anybody got A in SPM should be able to answer this question. Yeah, I think probably I haven't taught them soil chemistry, so they don't know which one is more electronegative and more electropositive. But obviously, it's the oxygen that carries the delta minus, right?
Yes, correct.
So,
So
student, listen up.
so as Dr. Yong said, so the oxygen will be slightly negative, whereas the hydrogens of the water molecule will be usually a bit positive. So when it's a bit positive, it can be attracted to the little bit of negativity of the other oxygen from the other water molecule, and this causes them to make a framework of water. So that's where our air dicincang takkan putus comes from. So because water makes a framework, so a framework of where the a bit positive hydrogen goes and be attracted to the little bit negative oxygen of another water molecule, and they form, this is just three molecules, so actually they form the, the let's say the lake, the water inside the bottle, the water when you turn on your tap and everything. But this bond is actually weak, but they are numerous. So that is hydrogen bonding. Now we talk about cohesion. So the term cohesion, for this, usually I don't like to use this image on the right. I use the image on the bottom of the slide. So cohesion is when the water sticks to another water molecule. So we are not talking about the bonding that is happening, but we are talking about, imagine I ask all of you to hold hands together. So cohesion, and imagine you are now the water molecule. So when a student and another student holds his hand, that is cohesion. So now imagine the student at the end is actually holding the table or the let's say this wall on his side. So that is addition. So cohesion is when water and water holds each other together. But addition is the ability of water to bond or to cling onto the surfaces of any material. So that's why my water is actually sticking to this. When I shake the water, you can see the water is actually sticking on these surfaces. So because of addition. And this too is how water actually moves inside the plant. So when we know xylem, right? So water usually moves it through xylem, but they move through cohesion. So as each one droplet is being pulled out from the stomata, another new droplet is being taken up by the fine root hairs of the plant. So that is cohesion, and due to their ability to stick to the walls of the xylem, so now we can create this piping mechanism where water is being moved inside the plant itself. Okay, now we are going to look at the stages of soil water. So there are 5 stages of soil water. First is saturation. Second is field capacity. We have wilting point, and we have hygroscopic point, and finally we have oven dry. So basically, for each of these is actually referring to the type of the soil that is existing with, and how the water will be during each of the situation. For saturation, okay, all right, I will just explain here first and then we'll move to the next slide. Okay, for saturation, imagine it's raining. So when it's raining, the soil pores will be filled with water. And now let's say it's about 1 to 2 days after rain. So water is still there from the rain, but some of the water has been evaporating, some has been taken up by the by the plants, some has been used by the microorganism, but there is adequate amount of water still in the soil, and that is what we call as field capacity. Wilting point is when, let's say, 2 to 3 weeks of no rain, there's no addition of water, and constantly water being used up by plants, by the microorganism, and water is also being leached out from the soil to the nearest water bodies. So in a manner, the water in the soil becomes very, very low, in which it is no longer available for the plants. That is what we call wilting point. So usually wilting point, the symptom is the plants will wilt because the water in the soil is not enough for to be taken up by the plants. And then we have hygroscopic point. So in hygroscopic point, the water now is only adhered as a thin film to the soil particles. So later I'll show you some images. So how, and you, it will, I believe it will help you to understand what I say by thin film that is tightly bounded to the particles. And in oven dry is a situation where in the soil there is no water. So there is no water, it's completely dry. So that is oven dry. Okay, so if you look at the first image where water is a lot inside the soil pores, so that is saturation. So this is usually because of it is raining or it just rained. The rain just stopped, so the water is completely, the pores of the soil is completely filled with water, but plants will wilt because of too much water. And usually in this saturation stage, water will be wasted. The water usually will be flowing out from the soil very, very fast. Okay, now we will, and let's say the water has moved up, summer has been taken up, and the sun has come up, causing evaporation of the water. So we will reach, the water will be lessening, but in a way that the water is now not so fast. The movement is not so fast, and it's held loosely by the soil for easier for plants to be taking it up easily. So that is where we call as field capacity. So field capacity, we can say that 50% of the pores is now filled with water and 50% is by air. But let's say the water is being leached out and being used and there's no rain for almost 2 to 3 weeks, then the water is going to go somewhere to permanent wilting point. So when it's permanent wilting point, meaning there is water, but it's very low. So meaning very low, the water that is existing in the soil is kept by the soil even closely. So it takes more energy for the plants to take up the water. And imagine the plant is already being wilt. So when it is already sick or already wilting, it surely doesn't have extra energy to take up the water. So when we reach permanent wilting point, usually the plants can withstand about 48 hours of this pressure or stress, and finally the plant will die off. So if no action is taken, about 48 hours, but depending on the type of the crops. Okay, so now we go more technical. So we have saturation, field capacity, wilting point, and hygroscopic point. So the most important thing here is the value. So you can use bar or kilopascal. So usually I use, my students like to use bar because the value is smaller. So 0 or negative 0 bar is equivalent to negative 10 kilopascal, and field capacity is negative 1/3, which is also equivalent to negative 30 kilopascal. So before I explain deeper, I want you to understand the value or the negative of negative sign of this kilopascal. So let's say we use kilopascal for the rest of this class. So we'll use kilopascal. You can also use bar. Is actually the same thing. It's just different units measuring the same thing. Okay, let's say we are using kilopascal. So you see so kilopascal is actually pressure. So when we measure pressure, we use kilopascal or bar. So you look at saturation, fuel capacity, wilting point, and hygroscopic point. So now I want someone to come and tell me which one has the highest pressure. Can anyone? Or maybe I can call out names. But I'm not familiar with you guys. So maybe Dr. Yong can handpick one or two students to.
Dr. Puvan, if
Yes.
you
Saturation.
click on, I think
So
Nolaili has already answered the question. So Nolaili, can you switch on your microphone and answer one more time?
I think the highest pressure is on saturation stage of water.
So okay, why do you think saturation has the highest pressure? Did you look at the values, or how did you make your answer as saturation?
Yes, because of the value.
So you're saying the smaller value equivalent to higher pressure. Is that true?
Because it's close to zero.
Okay. So here we need to understand the kilopascal shown here is referring to the how tight the water is being held by the soil particle. So if it's 10 compared to 3,100, where in which stage the soil is holding the water even highly, 10 or 3,100? Surely 3,100 is a bigger value compared to 10, right? So meaning at hygroscopic point, the water is holding the soil, the water is being held by the soil very tightly. Whereas at saturation, the energy or the pressure that the water is being held by the soil is only 10. Now the next question is, this is negative 10, this is negative 3,100. So negative 10 is bigger than negative 3,100. So this is what I think Laili, right? So this is why Laili said saturation is having higher pressure is because negative 10 is bigger than negative 3,100. And that's true in mathematics. But here, the negative sign, it's not telling us the magnitude. It's not saying let's say, it's not saying the value is big or small, but the negative here is only showing the direction. Let's say I'm pushing this table with 10 Pascal. So let's say I'm pushing this table with 10 Pascal. So we just write 10, right? So now imagine I pull the table. Instead of pushing, I pull the table with the same amount of energy that I used to push. Meaning I'm still using 10, but the direction, just now I was pushing it forward, right? Now I'm pulling it. So I'm pulling it with the same amount of energy that I'm using, but now to let know that the energy that I'm using is not to push but pull, I use a negative sign to tell us the vector. So in physics, you learn vector and magnitudes. So magnitude tells us the big or small, but in here, the negative refers to the vector or the direction. So meaning the negative here focuses on the pull of the soil particle, how strong the soil particle is pulling. So when can I put it as no? If I can just make the negative disappear, because the negative is only telling me that the water is being pulled by the soil particle. Let's say I want to talk about the plant. So now the plant is not gonna, it's gonna fight back. It's gonna pull back the water from the soil. So now the direction will change. Instead of moving, okay, so here this picture will help you to understand. So look at the brown particle. This is the soil particle. So this is the different levels of water. So the water that is very near to the soil particle usually is being pulled very tightly, whereas water that is far further away from the soil particle is usually loosely held. So to move this water, I need, it's being held for -10, right? So I need to give 10 kilopascal of energy. So when I say I is the plants need to make this value disappear. So it's -10. So the plant needs to give 10 pascal of energy to get the water. Whereas you compare to hygroscopic point, the plant now needs to give 3,100 kilopascal so that it can nullify this -3,100 that is being put. So you can see in this image, it's showing the direction. So instead of making the water move to the soil particle, I want the water to be moving further away from the soil particle. So the negative refers of the soil particle pulling it, not pushing it. So if you want to put, the soil particle is pushing it. But when we look from the plant side, the plant now needs to nullify this -10, -30, -1,500, as well as -3,100. So the negative sign here is only the vector or the direction. So I hope that negative is clear. So now, so when I say in which stage does the water is facing the highest pressure, is actually the hygroscopic point. So at the hygroscopic point, the water is experiencing 3,100 kilopascal of pressure from whom? From the soil particle. So actually all this kilopascal that is given to you, or the bar values are given to you, are in reference to the soil particle. So at saturation, because all the soil pores are filled with water, the 100% of the water, pore space is actually filled by water. There is no space for the air. So meaning we are looking at something like this. So there is, I think this picture is better. So we are looking at something like this. Look at how wet the soil is. So look, there is no film because instead all the sections are actually water. So it's purely water. So do the plant needs to give extra amount of energy to pull up the water from the soil particle? Very low, because they are lightly or loosely held by the soil particle. So the plant only need to give 10 kilopascal of energy to pull back the water from the soil particle. But at saturation, the problem is not with the pull of the soil particle, but due to the gravitational move. Because the water is very fast, it's percolating very fast, and so the tiny root hairs of the plants cannot manage to take it up as soon as the water is moving down very fast. So the problem is no longer with the soil particle strength, but the problem is with gravity. So that one we will look in the water movement in later parts. So at field capacity, the energy that the plant needs to give to fight back this pull of the soil particle is -30 kilopascal or -1/3 bar. So this is usually 1 to 2 days after rain. So the downward movement of water becomes negligible. So water is now no longer moves in due to gravity, it's not being filled. So this is usually the ideal type of soil, which is 50% of the pore space is actually water. So now water is moving, but a bit slower. So there is time for the soil, for the, for the plants to take up the water through its root. So water has moved out from the macropores and its place has been taken up by the air. So now we have 50% of pore space, water in pore space. And whereas the micropores is still filled with water and supplies the plants with needed water. When we reach wilting point, you will see a jump from -30 kilopascal to -1,500. So now the soil is no longer giving out its water, because itself, to retain its name as soil, it needs certain amount of water. So it no longer have the expense, or it no longer affords to give out water to the plants. So now the pool is very strong, and the water, if you look at this image, is much more closer to the soil particle compared to the water molecules that are actually further in field capacity as well as saturation. So this occurs where usually water is lost from soil due to transpiration or evaporation by the sun. And as the soil dries, the plants will wilt, because the amount of water in the soil is no longer available for the plants to take up. So plants will begin to wilt, but usually this occurs in the morning. At night, it regains vigor, because at night there's no sun. So usually this number will fluctuate during day and night, but that is only true for, let's say, 2 to 3 days, or usually it's about 48 hours, depending on the plants. But then it will reach certain time or certain threshold where night or day, it doesn't matter, it becomes wilt permanently. So that's where we get the permanent wilting points name. So actually, is there water during wilting point in the soil? There is. About 25% of the pore space is actually still water. So meaning soil can only give up from the 100% it has, it can only give up 50% of the water that it has. So the other 50% is for the soil itself to retain its moisture to become a good soil. So can we move even further? Can the soil dry up in a way where there is even less water? When wilting point, it is at 25% water in the pore space, but the soil can reach to hygroscopic point where it's only 15% of the water in the soil is actually filled with water in the pore space, meaning the others is air or it's just clogged. Okay, here water still exists, but the soil cannot give out the water. And in fact, even if the soil wants to give up the water to the plant, it cannot do it, because the water at hygroscopic point, the water that is being held by 3100 pressure by the soil particle, can only be moved if it changes from liquid to vapor. And surely soil in the nature or in the environment cannot make this liquid to become vapor unless it's by the sun, and even our sun will not dry up the soil until all this 15% is lost. And this is, you can only notice this if you go and do the sampling of the soil, you bring it to the lab, and then you do oven drying. So eventually all this water that is being held by the 3100 and more kilopascal by the soil particle can be removed by vapor, and now our soil becomes really dry with no water, and that soil is what we call as oven dried soil. So this is the image. You can use it to learn back what we have learned just now. So basically what I'm saying is saturated soil, the water is further from the soil particle, whereas wilting, also hygroscopic water, is displaced. So from permanent wilting point to dried soil is what we call as hygroscopic water. And that is what we are going to look at next. Okay, now we have known about the stages of soil water. So stages is actually the condition. Is it raining? Is it drought? Is it the plants are wilting? So did we put our soil in the oven to dry it? So that is the stages. But the type of water or type of soil water going to tell us what is the name of that water during that situation. So it's the name of the water during each situation. Situation is actually the stages, but the type of water, soil water, tells us the name of the particular water. So we can classify them using physical as well as biological classification. So we focus on the physical classification first. So we have right after rain until it drains out to fill capacity, we call this water as gravitational water. The name of the water from saturation to fill capacity is gravitational water. So gravitational water, the names comes from due to its the law that is governing the water during that situation. So the situation is from saturation to fill capacity, the stages. So it just rained, and let's say 1 to 2 days after rain, we are going to reach full capacity. So throughout that day, the name of the water is called gravitational water. And what does gravitational water does? So gravitational water moves in a way by where it is affected by gravity. The movement of this water is affected by gravity. So water moves downwards. Water percolates to the slope of the land direction, and water eventually will move up from the soil profile. So that is gravitational water. So gravitational water, it is held inside the macropores, the large size pores. So that is macropores. So the movement is very, very fast, very, very rapid. Now we have capillary water. So the name of the water right after we enter fill capacity up to hygroscopic point is known as capillary water. Capillary water is water that is held by the small pores, so the micropores, by cohesion and adhesion. So here we look at the cohesion and adhesion. So water and water holding each other, or the water sticking to the walls of the pores or the walls of the soil particles. So that is adhesion. So the movement of water here is according to the laws governing capillarity. So what does capillarity say? Water moves from an area of higher concentration to the area of lower concentration, or we can say from wet to the area that is dry. So in this timing, the water moves in a way where from region of higher concentration to region of lower concentration. So that's where the name capillary water comes from. And finally, we have the third types of soil water. In the physical classification, we have hygroscopic water. So hygroscopic water is water that forms thin layers. If you notice at the picture earlier, sorry, so it forms like thin layers of the soil particle. So they are very close to the soil particle. So and this name is from hygroscopic point up to oven dry. So as long there is water, we call it, there is name for the water. After oven dry, there is no name for the type of soil water, because when we oven dry, there is no longer water exists in the soil. That is for physical classification. If you are more interested into the biological classification, if you are more interested to the plants, so we only have two names, available and unavailable water. So available water is when water is readily available for the plants. Water in the soil can be taken up by the plants using just a bit amount of energy. So it's from fill capacity right up to before wilting point. So fill capacity up to before wilting point, we call this water as available water. Whereas from wilting point to oven dry, right before it's being oven dry, the name of the water in biological classification is unavailable water. So it's unavailable for the plant, because here the pressure that is needed to be given by the plants to take up neutralize the pool of the soil particle is negative 1,500 kilopascal and above. So plants can only use energy about negative 30 to negative 1,400 something, but this actually also depends on the types of plants. But generally speaking, is between fill capacity and wilting point. So one thing we are missing, notice that from saturation right before fill capacity, we don't have any biological classification. But to be honest, we can do some biological classification for saturation before fill capacity. So in your opinion, what do you think? what will be the name of the biological classification for that soil existing during saturation up to before field capacity? Can anyone try to answer?
Dr. Puvan, looks like nobody is answering, so I would like to try.
Okay, Dr. Yong.
If available, is for the plants to be able to taken up. More than that seems like drowning to me.
Yes,
Is that the word that you're looking?
yes, you are somewhere there. Yes, we have a lot of water here. We have a lot of water. But again, the water is moving very quick. So it's very rapid. Before the action of the plant to take up the nutrient, the water is already running. The water molecule that it was trying to take away is running away from it, from the roots. So although water is actually available, but in reality, it's very quickly moving. So that's why in this part, we cannot say it's available water. So in saturation to fill capacity, we cannot say it's available because yes, water is there, but it's moving very fast. So you imagine I have a bottle, I want to fill and I want to drink it for my whole day. I have 24 hours, but there is a hole here. So right before I come up to my office, the water is all dripping out. Yes, I have a bottle to store my water, and I've already stored water inside, but the water before I want to drink it is already gone. It's moving out. So can you imagine there's a big hole on your bottle and you just buy, let's say you go to Starbucks or Tea Life, and students like to drink these sweet drinks, right? Coffee. So imagine when the barista serves you the coffee, he makes a hole down there. Before you can take a sip of the water, it's already dripping out. So the one that is going to drink the water is not you, but the ants on the floor and the table. So that's why we don't have any biological name of the type of soil water at the saturation to fill capacity. Although by definition, water is a lot. So, but according to the law, when we talk about biological classification, we need to look to the respect to the plant. So that's why we cannot name it, it's available or unavailable. Because at sometimes, by chance, it may be able to take up a little bit. But that's why they didn't classify any name for biological classification for saturation to fill capacity. Okay, we just run through this. So gravitational water is water in excess of fill capacity. So water will drain freely from the soil by the forces of gravity. So gravity means it's very easy. I'll just hold this pen. When I remove my hand, what happens to the pen? So it will just fall down, right? So same, water, it will just flow downwards or it will move through the slopes and eventually being lost through the soil profile. So that's what's happened, that gravitational water. So even though the energy retention is low, it's only -10 to right before -30, but gravitational water is very limited to use the plants because it's moving very rapidly. It's only there for a quick time and it's gone. So imagine you are coming to class, Dr. Yong just comes in for 1 minute and he runs away. Before you can ask question, he just wraps everything and run away. So you cannot ask question. Yes, you have a lecturer, but you cannot ask questions. So imagine now Dr. Yong comes to class, he teaches you for 2 hours, he's staying there for 15 more minutes to answer your questions. So now you have time to interact with him. So similarly, the water is there. If it moves too fast, there's no time for the water to interact with the root or the root to interact with the water and pull it inside it. So that's what happened during right before fill capacity. Saturation to right before fill capacity. So and the name is gravitational water. And then secondly, we have capillary water. We can call this as cohesion water. So cohesion water is held in the pores of the capillary size or the micropores. So capillary water behaves according to the laws governing capillarity. So this is what I said. So usually water moves from region of high concentration to region of low concentration. And finally, we have hygroscopic water. So also known as addition water, because now the water is being held by the soil particle. This is the part or the molecule of water where it's very close to the soil particle. So they are known as addition water. So water is held tightly by the soil solids, and we can only move them when it becomes vapor. So it essentially non-liquid and moves primarily in vapor form. So higher plants cannot absorb hygroscopic water, but some microorganism activity have been found. It is latest research that's been done that some microorganism can actually use the hygroscopic water, even though the books of soil science are saying hygroscopic water cannot be used by any life forms. So here we have the types of soil water in infographics. So permanent wilting point, we have field capacity, and we have SWC. So this is gravitational water. So this is saturation water content, saturated water content. So the gravitational water, where the soil is too wet and it just drains out, especially at the root zone, because the roots cannot interact with the water, it already moves out. So this is the hygroscopic water, where there's only a tiny film of water that adheres to the soil particle. Okay, so this is little bit explanation about biological classification. So available water is retained in the soil between field capacity and wilting point. Remember, it's field capacity to wilting point, right before wilting point. It's not from saturation to wilting point. So because of the reasons that I've explained earlier. So unavailable water is water that is held at potential lower than wilting point. So unavailable water is not usable to most plants. In fact, you can just put it unusable for plants. Now we have reached the last part, the movement of the water in each of the stages and on each types, right? Just now we have known the name of the types of the water. So how does it move? So that is water movement in soil. We have three. We have saturated flow, we have unsaturated flow, and finally we have vapor movement. So first we have saturated flow. Saturated flow takes place when the soil are completely filled or saturated with water. Meaning, when does this type of movement occur? It occurs during the stages of saturation. So it occurs during the stages of saturation right up to before field capacity. So that is saturated flow. So we have long explanation here, but saturated flow means the movement is very fast. So under some condition, at least, takes place when the soils are completely filled. Under some condition, at least part of the soil profile may be completely saturated. So here, all the pores, macro, micro, is filled with water. Or I can say 100% of the soil pores are filled with water. So saturated flow starts with infiltration. So it begins when it rains and water seeps into the soil. So the downward movement of rain irrigation water from the top surfaces to the lower profiles. So when the profile is wet, the following movement of water through the wet profile is called percolation. So saturated flow resembles the flow of water through water pipes. Water creates friction as it flows among pipes, thus coarse soil permits more rapid movement or have greater hydraulic conductivity. So this is another term. Hydraulic conductivity means the ease of the water to move through the soil. So if it's easier to move, means it has lower water holding capacity. So higher hydraulic conductivity equivalent to lower water holding capacity. So which soil will have higher hydraulic conductivity? Sandy soil. So if the pore space are large and continuous, infiltration is very rapid, and also vice versa, meaning if it's small, then the infiltration is slow. So factors affecting rate of infiltration is texture, structure, organic matter, soil temperature, and agricultural system. And if you notice, it's just the explanation is just reverse of the water holding capacity. So one thing we can say is saturated flow, the movement of water is very rapid, and it follows the movement of gravity. It follows the law of gravity. Now we have unsaturated flow. When we say it's unsaturated, it's not full. There is spaces. So occurs when the large pores in the soil is filled with air. So meaning 50% of what pores is filled by air, 50% is filled by water. So the water only sits in the micropore. So most of the time, water movement takes place when upland soil is unsaturated. So the tightness with which water is held, the pressure just now we looked into, varies from time to time and place to place in unsaturated soil. So unsaturated flow occurs at pressure lower than negative 30 kilopascal. So at higher values or higher moisture content, hydraulic conductivity is higher in sand than in clay. Whereas at lower water potential, low moisture content, so hydraulic conductivity is higher in clay than in sand. So these 2 points may, if you look properly, it may confuse you. So what the statement is saying is, the first one, when soil have higher moisture content, meaning when the soil is wet, water moves very easily in sand compared to clay. This is true, right? Because that is what we have learned. So now you look at the second statement. When water content, when the water is lower in the soil, hydraulic conductivity is higher in clay compared to sand. Can you imagine this? Now, when water is a lot of water inside the soil, the water moves easier in sand compared to clay. And this is well explained because we know in sand we have large pores, so water will move very fast. But the second statement is where students may get confused, or sometimes they didn't even bother about it. So what will confuse you that is saying now water can move faster in clay compared to sand when water is low inside the soil. So to explain this, you need to imagine the soil particles. So imagine the soil particles imagine the soil pores or as rooms. So when I say rooms, maybe your classrooms or your bedrooms and everything. Okay. We are using pores and rooms as the analogy for the pore. So in clay, do you think the room size will be bigger or small?
Small?
Of course, small, because the size of the pore is small. We are just using the room as an analogy. In clay, in sand, the size of the room will be bigger. Okay. Now, imagine on top of the room, there is a gap for you to go through, and you can go to the next room. So, but for you to reach that height, to go through that channel, you need to fill up the room with students, let's say. So the students are actually the water. So if the room is big and the hole for me to move to the next room is up there. So if the room is big, of course, I will need a lot of students to come in. And then one student who, let's say, is 20, the capacity is 20. So at 20, the 21st student can go to the next room. Now, imagine the room is big. I will need a lot of students. That, let's say, about 50. Then the 51st can go to the next room. And when he reaches to the next room, there is another room that needs to be filled with 51 students to move to the other room. So now you translate it back to pores. So only when each pore is full, water moves to the other pores, right? So now imagine there is less water. There is very less water. So which pore will be filled first? The pores that are bigger or the pores that are smaller? When there is little water, pores that are smaller will get filled faster and water can move to the next pore or the neighboring pore. But for the sandy soil, the pores are big. Yes, the water can seep very fast, only if there is a lot of water. If there is very little water, we need to fill a very big pore before it moves to the second pore, before it moves to the other pore. So this is why we say at lower water potential or lower moisture content, the hydraulic conductivity is higher in clay. We are not saying the water is percolating out first. but we are saying the water is moving to another pore faster compared to that in sand. So that's why this statement is actually true, although it's a bit confusing. To be honest, this statement is more easier if I can draw it to you. So I'm not sure how we can draw this. Can you see if I draw on my screen like this? Can you see this?
Yep. Yep. Can.
Okay, I want it to be. Okay, so imagine we have a cup over here. So let's say I have channels to the second cup and so on. So finally, so if the cups are big, we need to fill the water up to here, then it can go to this second cup. Then when this is filled, it can move to the second cup. So now if we can do the same thing using a smaller cup, in which diagram that the water, more water is required. For sure, the one with the bigger cups. So that is what is actually being explained by that statements that I've just shown there. Oh, now I have trouble to erase it. Okay, clear all. So macropores, PS, so macropore space. So PS here is the pore space. So macropore space in coarse textured soil encourage saturated flow, whereas micropores in fine textured soil encourage more unsaturated flow. So in other words, I can say it this way. Water in micropores are the water that is available for the plants. Only up to permanent wilting point, right before permanent wilting point. So water in macropores, because it moves in a saturated flow, it moves very rapidly, it's unavailable for the plant. Although the pressure that is needed to neutralize the pull by the soil particle is very low. And finally, we have vapor movement. So vapor movement happens when the soil becomes too dry for water to move. So in vapor movement, water doesn't want to move. It wants to stick or to adhere to the soil particle. And it can only move when we change from liquid to gas. So vapor movement only occurs when water changes into vapor. So then it can condense and move up from the soil. So as a rule, vapor movement is very slow and moves very little water. So for a summary of water movement, so saturated flow is the downward movement of gravitational water, normally percolation, whereas unsaturated flow is the movement of water from moist to dry soil by capillary action in any direction. So it occurs more rapidly in, okay, this one I already explained just now. I'm not going to take that for so long. I've already taken up some time, right, Dr. Yong?
Yeah, we overshot by 20 minutes.
Okay.
I think you are towards the end, right?
Okay, maybe we can just do the, I can just show the example for calculation and then we can end it.
Okay, sure.
Okay, so here we have a sample question. The soil was sampled and weighed as follow. So immediately after rain, 250 gram. 2 days after the rain, 230 gram. When plants wilt, 200 gram. When the soil is air dried, 185. And when the soil is oven dry, is 170 gram. To be honest, we can answer this question by using the diagram that I shared earlier. We can use this diagram to answer this question. So immediately after rain is actually saturation. So this is actually telling, this value will help us to determine what amount of water at saturation. And 2 days after rain is flow capacity. When plants wilt is actually wilting point. When the soil is air dry, notice is air dry is hygroscopic point. And when the soil is oven dry is oven dry. So the formula we use, this is a moisture content calculation. Weight basis formula is moist weight minus oven dry weight over oven dry weight times 100. So how we are going to use this formula to calculate? Question is, percentage of water at saturation. So moist weight minus dry weight over dry weight. So for all the types of water, we're gonna use the same denominator. So we are gonna use 170 gram. Why? Because that is the oven dry weight, where there is no water. So now we want water at saturation. So saturation is this point, water at saturation. So this is 250 gram minus weight 170. Why? Because we want to know the full amount of water. So 0 to the full amount, 100% of water. So 250 minus 170 over 170, and we get the answer. Whereas for water at field capacity, we are going to look water from this point to oven dry. So how much is my soil can hold the water at field capacity? So 0 to, let's say I'm saying 80%. So how much is this? So 230 minus 170 over 170. So similarly for wilting point is the same. So we just take the value of the soil, so the weight of the soil during wilting point, and minus it with oven dry over oven dry. So for this first four section, we are going to use the same method. We are just looking at from 0 to the part that we want to look at: wilting point, full capacity, hygroscopic, or saturation. So now if we look at the gravitational water, I want to look at gravitational water. So I need to know gravitational water is not one point, but is gravitational water is saturation to field capacity. Meaning I want to look at how much water is actually this. How much is this? So for me to know how much is this, I need to remove from 100. From all, I need to remove this section. So how I'm going to do that? So it's 250 minus 230. So 250 minus 230, because these two already tells us, just now we already find out for field capacity, we can also find out for saturation. We can just straight out minus, but if you want to do it from start, you just do 250 minus 230 divided by 170. So you will get answer. But if you go and minus both of these, you will still get the answer. Same for percentage of available water. So available water is not referring to any points, but it's actually a section. So this section, field capacity to wilting point. So you just take the value amount of, the weight of the soil at field capacity and wilting point, and then minus them, find the difference over the oven dry times 100. You should get the answer. If I want you to find unavailable water, so you just go for the wilting point, which is 200 gram. Oven dry is 170 over 100 minus the difference and over by 170 times 100. You should be getting the answer for unavailable water. So I think this one you can try it by yourself. Okay, in how can we measure soil water content? So I believe most of you are trying, maybe will do soil research and everything. So there are actually 4 methods. The first is the gravimetric measurement. So gravimetric measurement is the most common method. So it's the simplest but the slowest. So why I say it's the slowest, you need to go and do the soil sampling. You need to bring back, put it in the oven. You need to weigh them and everything. Then you will get the water content. This is what we have done for the calculation just now. So we have weight basis, we also have volume basis. So I think this one you will cover in your lab session. Is it, Dr. Yong?
Yeah, in fact, it's going to happen tomorrow.
Okay, so that would be nice. So I won't touch too deep into it, because then you will look at the materials you are going to use this tomorrow. Okay, this is a bit more advanced. So this is called tensiometer. So this simply is a water-filled tube with porous ceramic cup and a vacuum gauge. So the soil will draw water out, creating the suction that the gorge measures. So in this gorge, there will be like an air bubble. So, and the soil will be pulling the water from this, the air bubble from this gorge. So the movement will then be translated to the reading at this scale, and that will tell us the water potential or the water tension. So this is what tensiometer is. And next we have even more, this is another method, is called electrical resistant blocks. So sometimes it's called Boyusk's blocks. So basically this is just two electrodes that is embedded in gypsum or fiberglass. It actually measures the electrical resistance. You plug it into the soil, these two electrodes. So from one electrode is going to send signal to the other electrode. And how does it send? It through electrical charges that moves inside the, moves through the soil moisture. So there need to be water for this to give a reading. So you normally use electrical resistant blocks for determining field capacity measurements or wilting point. You cannot use it for hygroscopic point. And finally, we have the neutron probe. So this is the high-tech method using neutron scattering. So a radioactive source emits neutron that collides with hydrogen atom from water. So basically, if the neutron collides more, it like experience more collision, meaning there is more water, because it will only collide with the hydrogen atom. So a neutron is very small size, which is also hydrogen having a very, very small size, so they can actually hit it. So this will actually tells us the behavior of the neutron stream will be translated into the reading of these measurements. So that is a neutron probe. So usually we use this for very high-end research. Well, normally it's not for research, it's for determining movement of like landslides or movement of soil water in area that is prone to landslides. What we call that, like the one we saw in Thailand recently, the whole area collapsed, right? So the areas that are prone to this, usually we can use neutron probes. So it's very accurate, but very expensive and requires experts to calibrate it. So that's all from me. So as a recap, I want to say that soil water actually supports plant life and also other soil processes that you have learned, I think, like hydration, dissolution, carbonation, and many more, actually, hydrolysis. And one thing we need to know about water, regardless of soil water or any other water, it is held by hydrogen bond and it undergoes cohesion or adhesion. So cohesion is water to water molecule. Adhesion is water molecule to surfaces of any soil particles or even your bottle surface. And I want to also say about the kilopascal that we use to measure how tightly the water is held. And the negative values is talking about the suction. The how strong is not showing the magnitude, but it's showing the vector. Who is pulling it? The negativity is showing that the soil particle is pulling it. So in order to neutralize that negative value, the direction, we look at the plant. So the plants will have positive value that is pulling the from the soil particle. And water, there is three ways for us to learn soil water. We learn through stages, meaning how the situation looks like. Is it raining? Is it 2 days after rain? Is it after a certain period of drought? And then we also look at the types of water existing at each of the situation. So that's where we can divide it to physical aspects or biological aspects. And in biological, we only have two, available and unavailable water. And finally, each types of water can actually move certainly. We call it saturated, unsaturated, and also vapor flow. So that's all from me. Do we have any questions, Dr. Yong?
Uh, well, from me, I would like to say something to the students with regards to what you have delivered just now, but perhaps maybe the students might have a few questions to ask you themselves. So perhaps we will like allow maybe one or two questions if there's If there are any from the students, if you would like to ask questions, switch on your microphone and introduce yourself. Okay, so I guess that sure, no question yet. If there's no question, then I would like to say something lah regarding Dr. Puvan's wonderful explanation of soil water. Actually, I do have pre-recorded lecture on the same topic, but it is very, very simplified. Very simplified, not as comprehensive as you do, Dr. Puvan. So good job on that one for extending the explanation beyond what I've had so far. Uh, Now, students, if you want to recap on Dr. Puvan's lecture, this session has been recorded and will be posted on my YouTube channel. So having said that, I would just like to ask Dr. Puvan, do you yourself have a YouTube channel or any social media that you would like the students to follow?
No, I don't have, doctor. But
Uh,
if they want to learn, maybe they can approach. Usually, I will just like students have questions, they just WhatsApp me and I'll just answer, or you can just email me the questions or anything. But I don't
okay.
have any contents.
Oh, so it's okay. So I will post this pre-recorded lecture in my YouTube channel. So students, if you want to recap, go ahead. Now, here's the most important thing. I know you want to listen to this lecture and perhaps you want to know which are the parts that are important for your evaluation. So number one, whatever Dr. Puvan told you about hygroscopic water, adhesion water, the gravitational water, plus the available and available the plant available and unavailable water plus the pressure will find its way in either your final examination question or in the test question. So I can assure you that whatever that you say today will appear because I already created the question and it's just you guys waiting for your time to answer this question. So make good use of his pre-recorded lecture later on. Study well. And for information, tomorrow's lab session will also involve um, most of Dr. Puvan's explanation on the calculation and also the classification of different type of moisture in the soil. So make good use of what you learned today. Make sure you write a very nice lab report regarding soil moisture and another topic, which is soil organic matter, tomorrow, because tomorrow's lab report will be the very first that will be evaluated. So make sure you give me your best lab report, yeah, student? Okay. So with that, I would think that that would be the end of our invited lecture. So the very first one for EVT 536 Soil Science and Analysis. So once again, thank you very much, Dr. Puvan, for accepting my invitation. So I will going to share your contact email, not your phone number, email
Yeah.
first with the students. So if they have any question, they will send you directly the questions through your email.
So that's I believe a student asked me about do I have a LinkedIn? I think yeah, maybe they can contact me through LinkedIn as well. So just search my name. It's Puvan Paramisparam. I think my name is quite rare, so you can find it easier.
Okay, so with that, I think that marks the end of our invited lecture. So to commemorate our invited lecture, so perhaps I would like to invite students to switch on their camera. No need to switch on your microphone, switch on your camera so that we can have a group photo. Let me change the view first, yeah? On. So we have like 50 plus students. So everyone switch on your camera so that you can capture your face. So yeah, this could be your attendance as well. So switch on your camera. I want to see your face. Okay, so are you guys ready? I can't see too many of you switch on.
Sorry, doctor, I don't have any camera.
It's okay then. So if you don't have any camera, then it's okay. I think I will have to like snap the photo right now. So every one of you, give me your best smile. Okay, 1, 2, 3. Okay, so that is all. Thank you very much once again, Dr. Puvan, for giving us
My
this
pleasure,
insightful
doctor.
lecture.
My pleasure. My pleasure. Thank
So
you.
with that, yeah, bye bye. Thank you.